Thank you, and good morning, everybody. I really appreciate the invitation to be here today. I have personally made a kind of mission for myself over the last couple of decades to talk about climate change from various perspectives, with the goal that I believe that a well-informed public will make well-informed decisions about the future. So I hope to accomplish that a little bit more today. My talk is called Climate Change in the Space Age. And as Pastor Amara read my biography, you'll now know that I've been, much of my career has been working with orbiting satellites to study various aspects of the surface of the Earth. Now, we all know that the climate is changing. What satellites are able to do is measure parts of this climate change that we would not normally be able to see with our ordinary ground-based observations. Satellites can give us a whole Earth perspective. So going from there, if you would please put on the opening slide, Matt. This is our Earth from space, one of the first photographs ever taken like this. It was on Apollo 17. Most of you remember the Apollo space program, I think. This was actually the final mission to the moon. The program ended after 1972. So I think this is a fitting cap to what was an extraordinary period of time in our country's history as we really led the way to exploring the moon and exploring outer space. It was given the name the Blue Marble, which I think is a very appropriate name because we can see from this perspective the sort of sapphire radiance of our oceans, the clouds, and the brown areas are the surface, the land surfaces of the Earth that we live on. And it also shows, as you can look at the various cloud formations in the southern hemisphere, how dynamic the Earth is. And it's actually the weather of the Earth that keeps it clean. Washes things away. So storms may seem like tragedy sometimes, particularly strong tropical storms and hurricanes, but they also have a positive benefit for us as a whole. Now on the next slide, I'm going to show you another picture much like this, but much smaller. It's coming from a new satellite that was launched by the United States about 8 to 10 years ago. It's called Discover, and it was a satellite that was first conceived by Al Gore when he was vice president in the late 1990s. There it is. His idea was that if we put a satellite far enough out into space, we could see the whole world at one time, and we could actually measure the changes in climate from that perspective. We can look at the radiation balance of the Earth, how much sunlight's going in, how much is reflecting out, and a number of things. So NASA, the National Oceanic and Atmospheric Administration, and the Air Force collaborated to produce this new satellite. When George Bush was elected president in 1990, his administration completely mothballed the thing and sent it into storage. And it wasn't until President Obama was elected that it was taken back out of storage and finished and launched into space. The interesting thing about this satellite is its orbit is in a very special place in space where the way the Earth's gravitational pull and the way the sun's gravitational pull are in balance, so the satellite can just sit in one spot over the Earth. And so here we can actually see the Earth turning, and because the satellite is so far out in space, it's about 4 lunar distances, 4 times the radius of the moon's orbit around the Earth. That's how far out in space it is, why you can see the moon tracing in front of the camera in this picture. So next one, please, Matt. Now, this is another perspective of the moon taken from one of our orbiting spacecraft. It's either the space shuttle or the space station. I'm not quite sure which one this photograph came from. But what I want to point out here is the bottom half of the picture. You see a lot of haze. That's the Earth's atmosphere. So the moon is rising up over the Earth, or the spaceship is rising up over the edge of the Earth, and just seeing the moon rise, I couldn't tell you which it is. But In contrast, we have the Earth's atmosphere right underneath it. And the important thing to make about a picture like this is that the atmosphere looks fairly thick here, but it's actually very, very thin. This area, part of the atmosphere we live in, called the troposphere, it's the lower atmosphere, is only about, well, it's about 18 kilometers thick. It's about the altitude of most jetliners fly at. And it's the lower atmosphere. It has very unique chemistry, including a lot of oxygen, which is what we need to use to live. But the interesting thing is that this is so thin that the ratio between the thickness of the atmosphere and the size of the Earth is smaller than the ratio of the skin of an apple to the size of the apple. That's how thin the atmosphere is. And this is where we live. Okay, we depend on the atmosphere for our lives and our livelihood. Next one, please, Matt. Okay, we know the Earth is warming. There's lots of evidence. Most of the evidence that's used to measure global climate change temperature are surface meteorological stations around the world and some satellites that monitor ocean water temperatures and so forth. This is a unique satellite that measures the temperature of the air with different kinds of instruments that are sensitive to the atmospheric temperature. And you can see that there's a trend here going from 1980 all the way up to the 2020. So this is a 40-year trend in atmospheric temperature measured by a satellite. And this basically averages the temperature vertically as well. So you can actually see more structure in the atmosphere from space than you can from ground-based observations. So this gives us a new impact, and you see some spikes in that graph, a couple places where it jumps up. Anybody have an idea what causes those? El Nino. Okay, those are episodes of El Nino which actually heat the atmosphere quite a bit, and so this satellite detects those spikes in the atmospheric temperature. Next picture, please. Okay, other evidence that the Earth is warming. This is the time graph of the concentration of carbon dioxide in the atmosphere. This began in the late 1950s when an enterprising scientist from the Scripps Institute of Oceanography decided, well, how accurately can we measure carbon dioxide in the atmosphere and watch how it changes? So he set up an observatory on the top of Mauna Loa in Hawaii, and this time series has been going ever since. And two things to point out about this. If you look at the beginning of the record, the first half, you see that the curve is relatively flat, and then it curves upward. So it's actually accelerating. The rate of carbon dioxide in the atmosphere is accelerating over time. So this is not a satellite measurement. This is a ground-based measurement. You also see along the bottom there, I put a little arrow that said this is the point in time when the Kyoto conference took place. And the Kyoto Protocol for addressing climate change took place. And funny thing is that that's right about the same time when the slope of this curve changed and started going up a little faster. I don't know how much of a coincidence that is, but it's an interesting observation. Now I'm going to switch to an very important satellite kind of measurement. This is a satellite that I worked on for a number of years when I was working with NASA. It's a satellite that measures the sea level around the globe. And the variations in sea level have a lot to do with variations in ocean circulation. And it's also a way to measure the average sea level rise as time goes on. So if we go to the next one, please. So here is a trace over time from when the first one of these satellite altimeter satellites was launched, which you see at the lower left corner there. It's got the red color to it. And then there were a sequence of 4 more satellites that piggybacked one after the other after the other. So we've been monitoring this global sea level now since the early 90s. And this is the trace of what it looks like. And you can see here that obviously the sea levels are rising. It seems like a small number, a few millimeters per year, but you add that up over many years, it's actually a substantial change in sea level. And this curve also changes with time. It gets more steeper. Not as much as that CO2 curve we just looked at, but the satellites actually give us a much more unique and accurate perspective of measuring sea level than we could possibly get using tide gauges and other kinds of measurements. The satellite covers the whole Earth every 10 days. So we get a snapshot of the sea level of the Earth every 10 days, and what you have here is those, accumulated in time, one after and one after and one after another. So that's one of actually the most important things about satellite observations is that we can look at global perspectives and ways that we just simply cannot get in that kind of detail from surface observations. So the next picture, Matt, is looking at the sea level rise from a different perspective. This is the rate of sea level rise, how it's distributed over the Earth, over the oceans. The areas that are colored orange and red are rising at the highest rate, and those that are colored yellow and green and blue are rising at the lowest rate. So we see a very uneven distribution of sea level rise that it's not like the whole ocean is filling up like a bathtub. It's going up and down in different places. But so the other picture gave you the global average. This shows how it's distributed over different parts of the ocean. And without that, able to see the whole ocean every 10 days and average those variations, we wouldn't be able to see something like this. You have to have the global measurement of the ocean, which is only available from a satellite. Next one, please. Okay, keep an eye on this. This picture of Antarctica is going to start moving. Now you see some things showing up around the perimeter that are colored purple. Now the perspective is changing as if you're flying over it. And what you'll see as you get up into the higher elevations of the Antarctic continent, they look like little streams. These are actually rivers of ice. The ice is actually flowing downhill. It's not water, it's actually the ice flowing downhill. These images were made by a satellite that has a very, very high resolution radar on it. And this radar can pick out very small objects on the surface of the Earth. And so by tracing the motions of these undulations and bumps and uneven patterns on the surface of the ice sheet, you can actually measure how it's moving over time. So this is really quite an interesting perspective of how dynamic Antarctica is. Okay, in the next picture, we're going to see, all right, so I want to show you a map of Washington State. Now, what does that have to do with climate change? Very simple. I want to use this as an illustration of a new satellite. Up on the top, you see it's called GRACE. That stands for Gravity, Recovery, and Climate Experiment. It's a satellite, very innovative satellite that was developed and launched. The first one was launched in the somewhere in the early 2000s. And it actually consists of two satellites flying in formation. So imagine the two satellites are flying over the Earth, one behind the other, in the exact same orbit, just trailing one after the other, and they're communicating with each other with radio transmissions back and forth. And with these radio signals, the two satellites can process how close they're getting together or how far, and when they're going further apart or when they're closer together. So if these two satellites are flying over the podium like this, as the first satellite reaches the podium, it feels a little bit more gravitational pull from this than it does the surface of the Earth way down there. And so it pulls ahead a little bit. And then the other satellite comes along and it starts to catch up as it feels it, and this one slows down over here. So by measuring, very precisely measuring the range between these two satellites that are going along, they can actually recover gravitational patterns over the surface of the Earth. So in the next picture, I'm going to show you a map of Antarctica and also Greenland, and you're going to see some changes in color as this animation goes forward. These all come from these gravitational measurements. So if you watch carefully, it should start changing color. Oh, maybe you have to push the start button on the video on this one, Matt. There you go. Perfect, thank you. Now you'll watch the colors evolve. Look along the left-hand side of Antarctica. You'll start seeing some orange colors show up. And if you look at the coast of Greenland, almost all the way around the coast of Greenland, you'll see these orange colors show up. Those orange colors are areas where the two land masses and ice sheets are actually losing ice. Okay? The ice mass is decreasing, and so this satellite system that can actually measure variations of mass at the surface of the Earth are showing where the ice is actually melting in Antarctica and where it's actually melting in Greenland. And you can see most of Greenland coastline is melting, particularly in the southern half and on the western half. In Antarctica, most of the losses over there on the lower left side, which is called the West Antarctic Ice Shelf, and it's losing ice the fastest. And then you can see a little bit of blue show up just to the right of that. That's an area where ice is starting to accumulate again. Now, I'm not quite sure why that's happening. There are glaciologists and specialists who study these things. I just really marvel at the technology that allows us to see something like this, which would not be visible if you were out there as the old glaciologists would be tromping around on skis and dog sleds trying to make measurements of the ice. So this is a very, very unique perspective of what we can see about how climate is changing in the world that we would not be able to observe any other way. Okay, we can move on now, Matt. Okay, now we're going to the other pole. We're going to the Arctic. And this is the Arctic ice sheet, ice cover. Now forget, the Arctic is an ocean. The Antarctic is a continent, but the Arctic is an ocean. It's an ocean that's covered with sea ice. And so this animation is showing how the sea ice is changing over the past 20 years or so. And the areas that are colored white are what are called multi-year ice, ice that lasts over the summer and freezes more again the following winter. And winter after winter after winter, these ice flows get thicker and stronger. But we're now losing the multi-year ice. And you see gray moving up and down, let's say, along the sides of Greenland and over in the Bering Sea near Alaska. Those are first-year ice that forms and then it melts away. Those gray patches are forming ice and melting away. But if you look at the ice in the middle of the Arctic, you'll see it's growing smaller and smaller. I can't read the year from this angle up on the upper left.
2006.
2006? Okay. So we're getting close, all right? So watch what's happening now. You see that the multi-year ice is vanishing. We're still getting first-year ice, which is the gray-colored area, but the multi-year ice is definitely vanishing away. Now, there is a recent study that was just released about 3 or 4 weeks ago by some scientists who use these kinds of observations along with climate models, and they're now forecasting that the entire Arctic may be free of ice in the summertime by mid-century, based on these kinds of observations. Without measurements like this, we would never be able to validate those climate models, and so we wouldn't know how accurate those predictions are. But by combining this with the forecast models, we get a much better idea of how fast things are happening. So this is one of the real important aspects of making measurements from space, to study the climate. Okay, Matt, let's move to the next one. All right, this is where I'd like to wrap things up. This is another view of the Earth from space. How many people here remember where they were when this particular Apollo flight took place? Oh, a few raises of hands, myself especially. This was over the Christmas holiday of 1998. And I remember I was home from college that year, and I was glued to the television all during the Christmas holiday. If you remember, the astronauts read from Genesis on Christmas Eve. But I think I marvel at this picture as much as the first one that we looked at, because it shows the Earth much more remotely than the ones where you see it up close as a full disk. And the awe and wonder is something that really is something I feel in my heart about how miraculous it is that we could even get this photograph, first of all, and that it shows how isolated we really are from the rest of the universe, and yet so full of life, not like the barren surface of the moon that we see here in the foreground. Okay, Matt, okay, I'd like to end with a few quotes. The first one is by Einstein. I can't read it quietly from here, but basically he says there's 2 ways to live your life. You can live it as if everything is a miracle or nothing is, or maybe I have it backwards. Yeah, nothing is a miracle or is. And I believe in the miracle part, to be honest with you. It's part of my faith. Another quote from Thomas Berry, different from the one that was just read earlier. Oh, thank you very much. This works better. Thomas Berry says, "The great work now as we move to the new millennium is to carry out the transition from a period of human devastation of the earth to a period where humans would be present to the planet in a mutually beneficial manner." Thank you. And the bottom quote there is from a very famous space pioneer. Have any of you ever heard of the Goddard Space Flight Center and NASA Research Center in Maryland? Maybe some of you have been through the Washington, D.C. area and have seen that. He said basically it's difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. He was a very, very forward-thinking person. He was the one who developed some of the earliest types of liquid fuel rockets that led the way to the whole space exploration process. So I'd like to wrap up here, and I'd like to express a bit of my own personal faith regarding the climate situation. I've come to a sort of a realization myself over the past few years that the issues around climate change, which for a long time were doubt about it, a lot of people who didn't want to deal with this were sowing doubt in the press and other ways of communicating the issue, that the climate change is not real and so forth. I think that, except for a few holdouts who just won't relent, the scientific debate about climate change is pretty much resolved. I think the evidence I've shown you today demonstrates that, and there's plenty of other evidence for that as well. But I think we're moving into a different debate right now, which is the political debate. And I think engaging in the political debate, something for me, calls my faith into play that this is something I need to do. It's a calling, if you want to call it that, to be involved in the political process of getting appropriate legislation through to reduce carbon emissions. And there's a lot of resistance out there. There's much to overcome. And I think that faith communities like this one, and like Grace Church, where I come from, are really a vanguard to this process. People coming forward to dealing with the climate crisis and preserving the earth as part of their faith is a real important force in this whole process.